Hello again. So today what I want to talk about is how we handle vectors that aren't going straight up and down. So it's not north, it's not south, it's not west or east. That basically the vector is somewhere in between. So kind of like the one that's on the board here. So we found that adding vectors that were both north was easy, or maybe one was north and the other was south. Those are easy. Those are simple to do. Connect them head to tail. You draw a line from the very beginning to the very end. You measure that distance if you're using the graphical method. And you apply your scale to it. But that has limitations. Doing that is limited. For instance, if the lines are really small or the lines are really big, it's a lot more difficult to measure. If the angle's impossible to measure unless you have a protractor with you, you don't get the accuracy with the graphical method that you do with the method I'm going to be showing you in the next few days, which is called the mathematical method. With mathematical method, I don't have to worry about measuring how long my vector should be using a scale and then applying that scale to the measured answer to figure out what the actual number would be. So mathematical, I think, is easier, and it's much more accurate, and I don't have to worry about my drawing so much. But we have the problem that if my lines aren't parallel to each other, it gets a little more complicated. So today what I want to talk about is, what do I do with a vector that goes off at some angle? It's not perfectly east and west. It's not perfectly north and south. Well, to make this easier, what we do is we break it into what we call components. So if I take this single vector, let's just say for argument's sake that if I look at a compass rose here where that's north, south, west and east. Let's say that the angle that's here is 35 degrees, okay? Let's just say that I have some vector, and I'll say that it's, let's say this vector represents 120 miles per hour at this direction. So kind of north of east is what we would call this. This would be north of east. Notice what that means is that you start by going east and then you turn towards the north. This would be north of east. So this last one is always where you start measuring your angle, and then you turn either north or south depending on what this says. So this is north of east. Okay, my problem is I really can't work with that vector if I try to add it to other things going off that angle. It gets a lot more complicated. So what we want to do is we're going to break that single vector into two components. And so as we mentioned when we were on the tile floor, going from here to here would be exactly the same thing as going first to this location and then to that one. So whether I take this path or whether I go in a straight line from here to there, I'm going to end up at the same place. I started at the same place and I ended at the same place. And so when we talk about displacement, it doesn't matter whether I do this path or this path, okay? I want to talk about how we can undergo a particular displacement. So, for instance, if I wanted to start at this location and then walk directly to my final location in a straight line, what I would basically be doing is I'd be arriving at this dot on the floor, and my displacement would simply be a measurement from where I started to where I ended, a straight line. That's one way to do it. But I could undergo a different motion. And really, instead of taking one path, it would be a set of two different journeys, we'll call them, to get from this location to that one. So instead of walking in a straight line, I would turn towards the north, and I would walk. I can even measure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 17 tiles from there to here. Each one's a foot, so that's 17 feet. Then I could turn towards the east, and I'd walk 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 more feet to get here. Now, was there any difference in terms of displacement? Was there any difference in walking from that location to this one directly in a straight line, or following the path that went to the side here and then turning and coming this way? I start at one place and I end at the very exact same place. There's no difference to it. So the point here is that I could do a displacement. There would be a single shot, straight line from start to end. That's a displacement. Or I could go one direction, then turn and come the other direction. Now, the distance I would travel would be different, but the displacement would be exactly the same. This is what we talk about when we talk about resolving vectors into components. This was a vector, a displacement. And when I walked from there to here, that was one component of that displacement. The other component would simply go from here to here. It's exactly the same displacement. And so these two dashed lines that you see here are what we call components. All right, these are components. And if I'm breaking up this single vector into components, this is a process that we call resolving a vector. Okay, or this is vector resolution sometimes because we like fancy words to make ourselves sound intelligent. Okay, so I'm going to want to break this into components. Now, if I want to figure out what these two components are, we have to use something that hopefully you've heard of before called SOHCAHTOA. Right? Now, if you remember this, I think you guys usually do this in geometry. So basically means that sine of the angle is going to equal the opposite side over the hypotenuse of that triangle. Ca means cosine of the angle is going to equal the adjacent side over the hypotenuse. And TOA means tangent is going to equal the opposite side over the adjacent side. Okay? I should have tangent theta here. Okay. So these things here, the SOHCAHTOA deal is just a way to help you remember them. Okay? But they're going to help us figure out what these links are. So for instance, if I look at my triangle here, what I'm seeing is that I have the angle here. This side, the longest side of any right triangle, is the hypotenuse. This side that's right next to the angle is what is called the adjacent side. Okay? And the side that's on the far side is the opposite side. Hopefully this brings back maybe bad memories, I don't know, from geometry, but we're going to go over it again. And so if you didn't get it when you were in geometry, maybe you'll get it now. Okay? So if I want to figure out what the adjacent side is, and I know what the hypotenuse is, what I would want to use, if I want to solve for adjacent and I know hypotenuse, which one of the three would be the best one to use? Well, I'm looking for one that has adjacent in it, which basically rules out sine. Sine's not going to get me anywhere because it doesn't have adjacent in it, and that's what I want. Tangent has adjacent in it, but the problem is I don't know what the opposite side is. I don't know what this is. And so I can't use this because I'd have two things I don't know. Cosine would be the one we would want to use to figure out what this side is. The reason being, I don't know adjacent. I do know the angle, so I'd be able to get this. I don't know what the adjacent is, but that's what I'm solving for. And I know what the hypotenuse is. So what I would say to solve for the adjacent side, I would say cosine of 35 equals the adjacent side, which we don't know, over the hypotenuse, which we know is 120 miles per hour. Now, I want to solve for adjacent. So that means I need to get rid of this 120. If I'm going to do that, I just multiply both sides. Okay? That's going to cancel it over here. And if I work out this side, I'll figure out what the adjacent is. So this would be cosine 35 times 120. I get 98.3. And this would be in miles per hour. Okay? So I know that this would be 98.3 miles per hour. Awesome. So we got one side. What about the opposite? What if I wanted to figure that out? Well, if I think SOHCAHTOA, I want the opposite. So which of the three is out? Well, cosine's out because I want the opposite, and there's no opposite here. Could I use tangent? I could, now that I know what the adjacent side is, but I would rather use a number they gave me, just in case I mess this up. I'd mess that up too. So I'm going to go with sine. So what I would say here is I would say that sine of 35 would equal, if you look at it, it's opposite over hypotenuse. We don't know opposite. But we do know the hypotenuse is 120 miles per hour. Okay. If I do my algebra, I get that 120 miles per hour times sine of 35 equals the opposite side. Again, all I did here was I multiplied both sides by 120 miles per hour. That would cancel it on this side, leaving me opposite, and leave me that on the other side. So if I do that math, and this is why we use calculators. $120 times sine of 35 equals 68.8 miles per hour. Okay, so I now know what this is. This is 68.8 miles per hour. Okay, so we now have the components. We have resolved that single 120 mile per hour vector into two components. So why would we need to do that? Let me get this cleaned up just a little bit here. And then I'm going to talk about why might we want to do that kind of a thing. Okay, so why would we want to do something like this? Well, let's just say, for instance, that instead of saying that you got some object that's moving 120 miles per hour at that angle, let's say it's a helicopter. I've got a helicopter that takes off from the ground and it flies at this angle and it has this speed, okay? I want to know how long is it going to take that helicopter to go 200 miles? Well, when you're measuring miles on a map, you're really talking about a horizontal displacement. You're moving across the land, which is generally flat. So this tells me how fast I would move across that map. I'm going to move at 98.3 miles per hour across the map. So to go 200 miles at that speed, at that angle, in 2 hours, I would basically go almost 200 miles. Okay? Maybe I want to know how quickly will I gain altitude. Well, I know the rate at which I'm going to climb. It's going to be at this speed going upward. Now, you're not going to be able to go for 2 hours if you're traveling at this speed upward because you'd be in outer space. But the point here is that instead of knowing something about how quickly I'm moving at some angle, this allows me to determine the rate at which I'm moving across the land or the rate at which my altitude is changing. It tells me different things about that motion. This is why we break vectors into components. So you might ask, well, why don't we need to worry about components? Well, we're going to be moving into a section here where we're going to start talking about projectiles. And the thing about a projectile, I mean, you see them all over the place. If I take my marker here and I launch it, it's a projectile, all right? As that projectile falls, what you'll notice is it starts off with one kind of motion, but then it kind of changes over time. So I'm going to do the example here of like a base jumper, all right? These guys that jump off of a cliff, they're wearing a parachute, they jump off a really tall cliff and they free fall for a few seconds and then the parachute comes out and everything, and they slowly descend towards the earth, okay? If I think about this parachutist though, as he runs to the edge of the cliff and he takes off, if you think about his motion, all of his motion the moment that he jumps off this cliff, all of it is in the horizontal direction. All right? It's all going this way. And what you'll notice is that, and we're going to go into this when we talk about projectiles, is that that horizontal motion never changes. Notice how all of these arrows, at least I'm trying to, all of these arrows should be the same length. You maintain this horizontal motion all the way through it. The reason is there's really nothing to slow you down if we ignore air resistance. You're going to keep moving this way at the same rate. But one new thing that happens the moment you jump off, that horizontal this horizontal vector no longer is the same vector or is the only vector that's acting. You also now have gravity. And gravity is going to start to pull you down. Okay? And as gravity works, you get pulled further and further down, faster and faster as time goes. Because you're moving quicker and quicker and quicker. These vectors represent how fast you're moving. So if I can add these two vectors together, what you'll actually will see as we move on is you will see the path that you take totally depends upon you taking this vertical downward motion. If I slide it over here, I connect it head to tail with these, it actually forms the path that you take. All right, if I slide this guy over to here, there's your path that you're taking. If I take this guy and slide it over to here, all right, that's the path that I'm taking. So what you'll see is your path depends on these two components. That's why we learn about components. It helps us make predictions about what's going to happen with projectiles.